I'd like to introduce Kieran, who is our speaker today. Kieran got his bachelor's in physics from the University of Maryland about 13 years ago, before he went down to the University of Miami to work with Professor David Nolan, who some of you might know in the room, working on forecasting tropical cyclone intensity in forecast models and looking at it in observations. And then after his PhD, which he completed in 2015, he went to Princeton University and the GFDL and worked there with Professor Guy Carpenter on looking at how intensification and rapid intensification in tropical cyclones changes or may change with climate change. And after his postdoc, he went and worked at BP for a couple of years, helping to advise them on the climate impacts on their portfolio. And then more recently is, let me get the title right, because I think it's a pretty awesome title. He is the Vice President of Climate Change Perils at Guy Carpenter, which is a reinsurance company that focuses on, and his work focuses on trying to understand the impact of climate change on those extreme events and what it means for impacts on society. So you can see he's kind of had a range of experiences already in his career. A couple of things that I do want to highlight. One of the most interesting things I found on Kieran's CV was that actually from 2014 to 2017, he spoke at over 20 different Rotary clubs in Florida, New York, and New Jersey about the impacts of climate change, about the impacts of storm preparedness and preparing for things like hurricanes. Which I think is a great use well, thanks to from me on the behalf of the scientific community of doing that level of advocacy as well as outreach, but also that he's received the Banner Miller award through the AMS, which goes out to a specific paper that's been published over the previous few years in the area of tropical cyclones and forecasting. So it's a very prestigious award that he won for, I think, some of his work as a graduate student. Is that right?
That's right. Yeah.
Yeah. So with that, I'll hand it over to Kieran and take it away.
Thanks so much. Yeah, Kevin, really appreciate the introduction. I'm really excited to be here. So thank you all. Today, I'm going to be talking about rapid intensification, and I'll just get the definition right out the way. I'm sure a lot of people in the room might have heard of this since it's getting a lot of attention. 95th percentile of all 24-hour intensity changes. So that's roughly less than 24 hours or 24 hours, 35 miles an hour increase or more. So that's how rapid intensification is defined. Perfect, thanks. So yeah, so the reason we care about rapid intensification, I'll talk about this more in the next slide, but I gave an image here, a video of Hurricane Ian from this year, which is a great example. For me, it's, I would say, the worst case scenario with a tropical cyclone. That's not an objective fact, that's an opinion. But the reason I say that is because you have a storm where you seemingly, with rapid intensification, might be a Cat 1, a tropical storm, a Cat 2 storm. And then a lot of times we see this overnight. You wake up and it's a Cat 4, Cat 5 storm. Make sure this microphone's working. Cat 4, Cat 5 storm with little preparation. It's the strongest storm. And in general, you have much larger losses as a result. So that's why I call it the worst case scenario. And then we have this quote here from recent Hurricane Ian, which really captures that, right? You have a certain amount of time to evacuate people. If you don't have forecast predictability or forecast anticipation of a strong storm, then you don't have enough time to evacuate people. Now, there's obviously a social science and physical science part of it, but rapid intensification brings these challenges upon us. So I kind of alluded to some of these already, but here's the reason why we care about this phenomena. First of all, the largest losses. Now, this is something that I've started to do some research on now, being in the insurance sector, reinsurance sector. Losses are really a lot more interesting to me. I use the data set from Wenkel et al., which is kind of a descendant of the Pelkey et al. Data set. And there's another data set also on this, which normalizes losses for per capita wealth, for population, for inflation, and it looks at loss, right? And what I did is I just basically, on the x-axis here, divided that by landfall intensity and then separate RI storms and non-RI storms. And what you can see just very quickly is that landfalling RI hurricanes have roughly about 5.5 times larger losses than non-RI. per knot of intensity. You also see that in recent years, those losses are going up. So immediately it starts to give you kind of some intuition why we care from a financial angle. From a strongest storms angle, I'm just quoting a paper or using a figure from Jiang Li in 2016, where she showed the lifetime maximum intensity of storms that underwent RI in red, and then that did not in blue. And what you'll notice is that those storms at the tail of the distribution, the major cyclones, Cat 3s through 5s, about 80% of the storms that reach those status have underwent RI. So RI is leading to some of the strongest storms out there. And then finally, this is a really, really important point. I'm using a figure from Travian et al. In 2020, where you see on the x-axis 48-hour forecast errors. And the y-axis, you have the number of RI or RW, rapid weakening events. And you see in red is the RI events, and blue is the rapid weakening events, and the solid line is Atlantic, dashed line is East Pacific. And what immediately jumps out is that not only are there larger errors, well, that doesn't actually jump out. It's harder to see that. What you can really see is the bias. So not only are RI forecasts 2 to 3 times larger an error than a normal forecast, their error direction or the bias is almost always an under forecasting. So there's this element of under preparation. You're expecting something that is a lot less strong than what you actually get. And as a result, that's leading to vulnerable communities.
So before you go to the next slide.
Sure.
The one additional thing that could go wrong is that the mic actually fell off the cliff, so it's hanging down with your feet.
That is
So we finished the trifecta.
okay, that's new. See if I can get that back. Sorry about that. All right, let's try that again. Here we go. All right, so now that hopefully that gives you a little context about why we care about rapid intensification, I'm going to go through a few topics and really take you on a journey of the last, I mentioned on the first slide, 3 papers that I've done, and start kind of in a funny place, which is the future, because that's really what prompted me to look at this challenge of rapid intensification, something that came out of some climate model projections. Then based on that, I'll take you to actually the past, and based on what we saw in this model result, do we see in observations a similar connection to climate change, or is it just kind of natural variability? And then finally, based on what we see in the past, can we explain it with some of the environmental trends or environmental situations around storms, and whether or not climate change is contributing to that as well? So as promised, future projections first, a little out of order, but this is the journey that I went on to look at this problem. And it started with me looking at some model output from the high resolution forecast oriented low ocean resolution model, mouthful, sorry. From now on called high floor, so it'll be much easier for everybody. So high floor is a 1/4 degree atmospheric model, 1/4 degree by 1/4 degree, and then a 1 degree by 1 degree ocean model. It was looked at extensively at the Geophysical Fluid Dynamics Laboratory by myself and others. It's unique in the sense that it is a coupled climate model that's able to capture category 4 and 5 storms. It is able to represent inter-annual variability very well of the climate and its impact on TCs, tropical cyclones, and then also in the Atlantic does very well at look at also capturing interannual variability and how it connects to hurricanes. And as a result, in this first 2018 study, we looked at 3 experiments. One, the control experiment based on 1986 and 2005 temperature, land and ocean temperatures. We looked at a near-term experiment, which was representative of 2016 and 2035. And then we looked at a late experiment at 2081 to 2100. And we found something really interesting, which is if you look at not just the number of storms, but the ratio of storms that were under, or the ratio of 24-hour intensity changes that were meeting that RI cutoff, right? Or also known as RI ratio of storms, we saw that the percent was increasing. So on the top of this graphic right here, you'll see that we have some reds and blues. A red, it indicates an increase in the proportion of storms that undergo RI, and blue is a decrease. And you see it's almost all red, and that's in the near term period. The white X's represent non-significant grid boxes that are 5 degree by 5 degree. And then if you go to the bottom, you see 2081 to 2100, and you see a further increase in intensification due to climate change in this high floor model. So that got us thinking, okay, well, what does that mean? Why are we seeing that? Is this a real signal? We don't have a lot of climate models that capture RI. Is this a valid signal? And just to kind of put this image another way, I did a log 10 plot of 24-hour intensity changes in those 3 simulations. And you'll see that the probability of the higher intensity changes goes up with time in this model. And in fact, I just picked one cutoff here, which is 80 knots. And there's 24 cases of 80 knots or more increase in 2081 to 2100. There's only 4 cases in the present day. So just started to kind of scratch our heads. Is this a result that's meaningful? Is this something that we see in observations? At the same time, almost exactly, maybe a little bit earlier, Kerry Emanuel was looking at the statistical dynamical model and looking at the question of rapid intensification. And he saw that actually, if you look on the left-hand part of the slide, he looked at NCEP reanalysis in the black line, and you see the return period on the y-axis, the x-axis is intensity change right before landfall. And then he saw that his blue simulation of the past was very similar to what we saw in the reanalysis. And then he looked at the end of the century and he saw that all those return periods basically got shorter for the highest intensification before landfall. And then when you see this plot, then you start to really kind of, it gets your attention. He was giving an example from 2086 of one of the storms in his model that affected the Galveston-Houston area and underwent a intensification of 104 knots right before landfall. So you can think of that event as like, well, it's a 1 in 100 year event, but if those types of events are possible or getting more likely, what does that mean for loss impacts, especially with all the things associated with RI? So as a result, that prompted me and others to look at what is happening in recent years. Do we see observations in the connection to the climate change signal that's similar to what we see in the high floor projections? Now, before I switch to that section, were there any questions or comments or thoughts on that first part? Or is it pretty straightforward?
Where did the increase the speed of 35 knots come from?
Yeah, it's super arbitrary. So the 90, it just basically someone one day said, okay, 95th percentile of 24-hour intensity changes in the Atlantic is roughly 35 miles an hour, or 30 knots. And that's rapid intensification because it's 2 sigma. Actually, in the West Pacific, it's closer to 40 knots. So their definition of RI is actually different based on that quantitative measure, but that's what we normally use.
Start from relatively low speed and add 35 could be quite different damage than if it was at the highest speed and add 35.
Yeah, no, it's 100% true. And actually, it definitely does matter, and that's an important thing for losses as well, right? I think when I'm starting to look closer at that loss data, I'm starting to differentiate, trying by intensity at landfall, but also the amount of intensity change and how far it happens before land, because you can see that connection as far as in preparation and what it means for a loss perspective.
But going back to the Lee et al. Paper that you mentioned.
Yeah.
That suggests though that, right, the difference between major storms and not major storms is the likelihood of going under rapid intensification. And so thus it's to Malcolm's point, thus that most of the time when you're undergoing rapid intensification, it's occurring from a relatively weak storm, like a hurricane category 1 or weaker. Right? Is that right? That's more of a question.
No, yeah. So it's this actual question. There's no straightforward answer to this. And I mean, I think the reason why it's not straightforward is that we see RI happen just based on that quantitative definition, we see it happening from a storm that is 30 knots and undergoing genesis. And those are actually the hardest, right? Is that you don't even have a vertically stacked cyclone, but then you overnight, you'll get not only a circulation around the center, but then you'll get additional intensification. That's really, really tough. But then you also have cases where you have it vertically stacked. And these are actually a recent study that I saw at AMS this year, which showed that those have the highest chances to get to the peak intensities. If you have the vertical stacking, that's normally when you see RI going from, you know, not just 30 knots, but up to like 70 to 80 knots in 24 hours. So there's actually starting to be a discussion of there's different flavors of RI. If you have these like marathon cases versus sprint cases of RI, and what's the leading cause of that? Any other questions? All right, so transitioning into observation. So I rely heavily on two observational data sets for this discussion. One is the ADT HRSAT, or the Advanced Dvorak Technique data set. What's unique about this data set is that it uses the same Dvorak approach to estimating intensity from satellite data. So it takes satellite imagery and purely based on satellite imagery gets a intensity estimate. Now, as a result of that, it's both temporally and spatially homogeneous, which means that throughout the globe and throughout time, the technique to capture intensity does not change. And then, of course, there's the IBTRAX approach, which is across the world. There's different forecasting centers. Their observational tools change with time. They get better with time. They're more accurate for a given storm, but there's both temporal and spatial inconsistencies. You'll actually see a lot of papers just use IBTRAX to come up with trends. The issue with that is the fact that these observational inconsistencies are sometimes leading to spurious trends. For a given storm, intensity estimate is probably better for IBTRAX, but when you're trying to understand how things change, ADT HRSAT's a lot better. Now, just as a quick background, the storms that we include in the analyses, we're really focusing on tropical systems. So we're trying to pick certain latitudes that are closer to the equator. We're making sure that it's only over the ocean during the period of interest. And we're also making sure there's a certain longevity because of the fact that we see storms that have shorter lifetimes. The observational detection of those storms are a lot different now than they were in the past. So just going straight to some early quick results here. We're doing a Atlantic and global quantile regression here during that period of interest. What you see on the x-axis here is quantiles. On the y-axis is the slope in knots per year during that 36-year period. And you see in blue IBTRAX and in red ADT HRSAT. Now, globally, there's a large discrepancy, but the picture remains the same. You see a decrease in slope or a negative slope in the lowest percentiles, an increase in the highest percentiles, both in the Atlantic and globally. Some of the differences between the global picture and the IBTRAX versus ADT HRSAT, we talk about a lot in the 2019 paper and what's driving that. And it's largely, we think it's because of the observational changes globally. In the Atlantic, the observations have stayed much more consistent with time. And as a result, we think that that's why there's a lot more similarities. I'll just mention, just so it's clear, we see a 0.1 knot per year slope, which doesn't sound like a lot, but over 36 years, you think about your 95th percentile, that's roughly close to 4 knots over that period. And that means that basically that definition of RI has changed by about 4 knots during that period, according to ADT HRSAT. And IBTRAX, it's closer to 10 knots, what they're suggesting. So definitely not a massive signal, but definitely a signal there. And it's over a long period of time, or a long-ish period of time. Australian and West Pacific, similar story. West Pacific has the largest signal in ADT HRSAT out of all the different basins. And as a result, that gives us some confidence that that is a robust trend that we see in that basin. Australian, largely, actually, I think it's the biggest change or discrepancy between ADT HRSAT and IBTRAX. Again, largely observational observational spurious issue there. So just to give you a kind of, there's quite a few more studies, but a recent study which also looked at this intensification picture in the Atlantic, this Bulgaroo study from Pacific Northwest Laboratory. You'll see that they had a similar outcome in the Atlantic. They see a increase in intensification, especially something that's a little bit interesting for us over here is that the largest increase in intensification was in the Atlantic coast of the US. They have the biggest uptick in the amount of high intensification events. They divide it into the Gulf and the Atlantic, and that's where they see the largest. They see a overall trend that's very similar to us during the period. And I guess if I can, this might work. Yeah, so this is a bin for 0 to 7.5 knots per 6 hours. That's 7 to 7.5 to 15. We're talking about knots per 6 hours. And the green is the difference between the period 1999 to 2018 and 1979 to 1998. So similar picture in the Gulf, kind of interesting for that 0 to 7.5 knot per 6 hour bin is actually a decrease, but the 7.5, the most extreme RI events are actually significantly higher or happening significantly more in the later 20-year period in the Gulf as well. So very consistent to the picture we're seeing. So going through that journey, we first look at the projections, then we look at observations. We're saying, oh, there's a similar trend here. I guess the next question becomes, well, are those trends based on natural variability, or are they something that has an anthropogenic signal, right? Is this something where, for example, in the Atlantic, we have a switching of, well, now it's a bit more controversial, but an AMO or a reduction of aerosols, is that explaining it? Or well, sorry, is an AMV type signal explaining it, or is it something like anthropogenic greenhouse gases or aerosols changing? So before I get into this section, any questions on the observational trends that I showed you?
So for that last study you showed,
Yeah,
the GNL, what observational data set are they using there? Is it
purely IB tracks. Yeah.
so? But that's the one that showed the bigger change from your study, right?
Well, it's interesting because IB tracks shows for the Atlantic
that's
a
right.
very similar trend to ADT HRSAT, and so that's the one where we're, we gravitate in our study to the basins where you see that agreement, because likelihood of the observation, and the fact is in the Atlantic we've had high-ish resolution satellites during the whole 1980s and beyond, so you're probably having a good idea of your intensity of your storms for a while, whereas in some of the other basins there's been big upgrades to satellites. There's been some changes in their detection algorithms, and as a result, we're not as confident in those results. The Atlantic is one where, and why we show it, we have some more confidence in it. Any other questions? All right. So for this portion, we're going to go back to high floor to answer this question, and I'll mention the big caveat here is that this is one climate model. We need more climate models or more approaches to understanding what is normal rapid intensification behavior, what is normal climate variability with hurricanes. These results are caveated with the fact that we're saying that, HI4 does a pretty good job based on the metrics we've looked at for simulating hurricanes and rapid intensification, but it represents one model's representation of that. And for this part of the study, we looked at 4 control simulations, which are fixed at years 1860, 1940, 1990, and 2015. We use the 1860 simulation here because it provides, it's fixed at the anthropogenic emissions levels at those different years. We use the 1860 simulation because it provides a longer data set, and each simulation we split up into overlapping 36-year periods. In the 2019 study, we did non-overlapping and overlapping, and it showed very similar results. So we're using the more expansive data set here. So to capture what natural variability is like, we calculated all the slopes of the 36-year periods in RI ratio and compared that to observations. And I'll just mention before showing the results of those comparisons that we didn't just use high floor data by itself. We also did a bias correction there. And the x-axis here, you'll see 24-hour intensity changes plotted. On the y-axis is the log 10 probability. And the PDF of 24-hour intensity changes plotted for AT Hersat, IB tracks, high floor original in red, and then high floor quantile delta mapping in magenta, and then bias corrected quantile mapping in green. And we use the QDM approach in magenta because of the fact that we wanted the rapid intensification profiles to be very similar to observations, and so that the trends in those intensifications were going to have the same magnitude of what we see in observations, or at least try to have the same magnitude. So we use a bias corrected version for this analysis. And as a result, we hope that we have gotten, for our 36-year periods, a representative observation of what is actually reality of variability in intensification. And here are some of the results. We looked at, you can see in gray, we have a PDF type plot on top of all the different slopes from the high floor model. In red and blue are overlaid IB tracks and ADT Hersat trends that we saw during that 36-year period. And the bottom of this graph, we have box and whisker plot with those observed trends marked. And what you'll see is that those observed trends based on high floor are outside of the normal natural variability, or the 95th percentile of what we saw in the high floor model. So these are very unique trends globally compared to observations. And then, excuse me, these are very unique trends, what we see globally compared to what high floor says is normal natural variability. And then in the Atlantic Basin, a similar picture is drawn. You'll notice that the slopes are larger. There's a broader distribution, and that the reason for that is because in the Atlantic, you have more variability about how RI can change with time. And then the box and whisker plot at the bottom again shows that they're outside of the 95th percentile. There's a few instances in the model where you have higher slopes during a 36-year period, but there's only very few, right, out of 1,400. And then West Pacific is a much larger trend. Our high floor model doesn't even have observed trends during that control simulation, the magnitude of ADT Hersat. Again, it's showing that the natural variability as represented by high floor, the observed trends are outside of it. And so these three basins suggest to us that we're seeing, at least as defined by high floor, trends that are really outside of normal natural variability. Now, maybe based on what I said about it being one model, you're not convinced that, okay, we know what normal intensification behavior or trends are, right? So that's when we went to this final piece here, which is, well, is there an explanation for there being an upward tick in intensification, right? Can we understand what's potentially driving this to get us some confidence in those results that are shown by high floor? So now we start to look at the environments around storms as well as the tropical mean environments. And one of the unique parts of our work is that we look at storm local environments, which has not really been done yet. A lot of studies have looked at, for example, okay, during the tropical months in the northern hemisphere and southern hemisphere, whether that's July, August, September, things like that. Okay, what is the mean behavior of the environment? We look at a box around the storm center and understand what the storm is actually experiencing with time, and understanding if that's changing in conduciveness for intensification. So we look at, to answer that question, we look at two reanalysis data sets, ERA5 and MIRA2. we look at 4 environmental variables around the storm: sea surface temperature, wind shear, relative humidity, and potential intensity. Do people in the audience have people heard of potential intensity, or should I talk about that really quickly? Yeah, so potential intensity really is as a overview is basically a good measure of the disequilibrium between the surface and the higher levels of the atmosphere. So Kerry Manuel, when he came up with this theory, was basically using that difference between the surface of your tropical cyclone and the outflow layer as a idea of what the kind of potential this storm could get to. Because that disequilibrium in a use a Carnot engine approximation, which means basically that could drive an intensity change. So higher potential intensity means higher chances for a storm to get to a larger intensity based on that theory. Now, there's a lot of approximations there. He assumes an axisymmetric or perfectly symmetric storm that's kind of in a steady state, but it's done a very good job at kind of, for the right or wrong reasons, understanding how far or how fast a storm can intensify. We use values centered around the storm. I mentioned that already. We paired each of those data sets, each of those reanalysis data sets with the storm intensity change itself. So we kind of see what the drivers are. And then we use spectral filtering to remove spatial scales associated with the storm circulation and really preserve the environmental signature. Now, I mentioned those 4 variables. To determine this critical environmental thresholds for each basin, we define a critical threshold as the environmental parameter value that yields the overall probability of a 24-hour intensity change exceeding 30 knots. So it's using logistic regression to solve for the values of each of these 4 parameters that yields this RI percentage. Now, Kaplan and De Maria, they define critical thresholds a little different way, and other studies normally are looking at a threshold which is like, here's the mean value of environments when a storm undergoes RI versus not. This is a much more kind of methodical way to do it. And it's really just used as a way to differentiate situations where storms intensify and don't, and see, does it matter if these thresholds are exceeded or not? And this graphic answers that question a little bit. What we plot here is for each of the different basins, Atlantic, East Pacific, West Pacific, South Pacific, Australian, and global, what is the probability of RI if the environmental threshold is met or not? So the first one on the left is shear. So if it's below the wind shear or wind changing with height value. Second one is SST, sea surface temperature. Third one is relative humidity. And fourth one is potential intensity minus current intensity. And what you'll notice very quickly is that when a storm meets these thresholds, there is a higher chance of it undergoing RI. And you also notice that the furthest right column is the highest typically for most basins. And that's because potential intensity minus current intensity is the best predictor of RI just about for most of these basins. Now, the second thing that De Maria and Kaplan looked at, and we did here, is there a nonlinear relationship between thresholds being satisfied and the probability of RI? So what we did is we plotted for each of the basins, how does RI probability change with the number of RI thresholds being satisfied? And if you look, let's just pick green star, which is global. When you see 1 or 2 being satisfied, it's like 3 to 7%. But by the time you have 4 thresholds satisfied, or this convergence of a lot of favorable environmental variables working together, you see the probability is closer to 22%, which really captures something that we see a lot, is that there is really a nonlinear relationship. When you have all these boxes checked for RI, there's a noticeably more or higher opportunity for this storm to undergo RI. So we're seeing that here, and it kind of insinuates there's a bit of a threshold behavior with RI, right? Rather than just a purely linear, that things are just kind of slowly getting more and more favorable.
So, but it doesn't go to zero. So.
Yeah.
Does that mean that either you're missing a potential environmental variable, or does it mean maybe your thresholds are slightly?
Well, no,
What is the implication of that? Because that suggests that there can still be cases of RI
yeah.
without satisfying any of these requirements, right?
That's right. Yeah. So that's as expected, because the logistic regression is solving for a situation where you are trying to pick a environmental cutoff between RI and not RI, but it doesn't mean that that's the ideal number, right? It doesn't mean it's a firm number. It's just basically solving that equation. So there are situations, though very unlikely, and they're obviously going to cause forecasters incredible difficulties. And I think understanding some of these situations better is a whole project in itself, where nothing looks right for RI. You have high shear, low relative humidity, low SSTs, low potential intensity, and somehow it undergoes RI. I guess that's as much of a result as the fact that, yeah, when you have them all converging, then you have a significantly higher probability.
But with the number, like the sample number for these.
Yeah.
So that's kind of like the background almost probability of RI, and the full data set is.
So the background probability is this right here.
Oh, that's right.
That's the global, yeah, I should have mentioned that. That's the global average of RI based on the 30 knot definition. And that goes back to my point, which is it's supposed to be roughly like a 5% of RI at 30 knots. But actually that number for global is higher, and that number has gotten higher with time, right? The definition of RI now, even in the Atlantic, is not 30 knots. It's higher than that, and globally, it's definitely higher than that. So based on that, we wanted to look at the number of fixes achieving 3 or 4 environmental thresholds or 0 or 1, and see if those, not only do we look at just linearly how the environments have changed with time on average, we wanted to look at how many times these perfect situations for RI have changed. And the 3 or 4 thresholds, the black line and the black dots capture that. So we see globally in the Atlantic that these situations where 3 or 4 thresholds are met have gone up a lot. In the Atlantic, for example, it's basically doubled over the last 36 years. So going roughly from about 20% of the time, 3 or 4 thresholds are met, to about 40% of the time. So there's a lot more of these, four of these variables are all converging to nice values. And likewise, vice versa, 0 or 1 thresholds being met have gone down a lot. So a lot of these very negative situations for intensification have gone down as well. Yeah.
Just for storms that are undergoing RI, or for all storms?
That's for all storms. Yeah. This is just, we're not differentiating in this picture between storms that undergo RI. This is just purely an environmental look at storms overall. And then to kind of capture that another way, we looked at this plot, which I'll take you through, which is looking at the probability of RI versus sea surface temperature and potential intensity. And on the left, we have global and the Atlantic on the right. And what we plotted here is we did a logistic regression to solve for the probability of RI based on different potential intensity and SST values. And you can see the probabilities are mentioned here on the right. And you'll see that there's different red plus signs on this image. We looked at every tercile for every 12-year period between 1982 to 2017. And we plotted the numbers of the terciles here. So you can see that globally and in the Atlantic, that the terciles are moving across contours to more potential intensity and higher SST values. And it's really obvious in the Atlantic that it's moving to these higher values. So just another way to capture these environmental conditions, especially thermodynamic conditions, are becoming a lot more conducive. And just to kind of bring up that study and show a similar picture here, the Balaguru et al. Study also looked at, again, specifically the North Atlantic, and looked at environmental variables like potential intensity on the left, shear on the top right, vorticity and relative humidity. And the black X's, they're kind of hard to see, but those are significant areas. And you'll see potential intensity is really standing out. And the slopes here is like around, the reds and oranges around 0.15 knots per year. You'll see that there's a lot, especially near the coast, of higher potential intensity values. The blues are lower shear values, and the reds are higher vorticity. Blues are higher relative humidity. So you can see these coastal areas, and they bring up the Atlantic coast a lot, because you see actually some of the strongest signals there. Lower shear, higher relative humidity, and higher potential intensity. They're all converging in those areas around the Atlantic coast. So another kind of similarity between our results, really kind of that right graphic really capturing what we're showing there. Now we shifted focus, where those were all storm local plots for what I showed you for the work that we did. Of course, climate models, you can't really capture 6-hourly intervals, or you can't really get that resolution that you have around storms that you see in the reanalysis data. So we did also say, okay, do those trends we see in the storm local environments, are they reflected in the tropical mean? So the top, we looked at relative humidity. Second graphic is wind shear. Third is sea surface temperature, and the fourth is potential intensity. And what we see is that a different picture for different variables. Relative humidity is a complete puzzle. You have significant trends up in ERA 5, significant trends down in ERA 2. The differences are quite large, and so we don't really have a concise picture from a tropical mean perspective. Shear, much more agreement between ERA 5 and ERA 2. Not a significant trend overall, but there's a decreasing values, but it's not significant because of the variance versus signal. SST and potential intensity, we do see a significant trend. We see an uptick in both reanalysis data sets, and we see them in both hemispheres as well. So you're probably wondering, well, are these natural variability driven, or are these something to do with climate change? And so to answer that question, what we did is we looked at CMIP6 tropical mean values of August, September, October, SST and potential intensity, shear and relative humidity. The top graphic here, let me take you through it. These are the trends in the blue, historical natural runs, gray, historical all-forcing, and orange, historical GHG runs. I have put on this graphic ERA 5 trends and ERA 2 during the period 1982 to 2014, which is supposed to represent what we see in CMIP6 as well. We use the same period. And then we did a equally weighted ensemble version of that, which means that some of these ensembles or simulations have more ensemble members than others. And we wanted to weight each ensemble center the same. So we did that over here. And what you can see immediately from the SST graph is that there's almost no trend in the historical natural. But when you bring up GHG and historical all forcing, you see an upward trend. The reanalysis data sets agree with those trends. It's a very clear picture, right? Potential intensity is a lot more nuanced. You do see that the gray PDF shifts to the right, which suggests that historical natural is different in slopes compared to historical all forcing. But those, even though these trends are significantly different, the reanalysis data is way outside of it, right? The reanalysis data set is showing a trend of almost 3 times, actually, if you do the equally weighted ensemble. So you start to wonder, okay, well, something's going on there, right? The CMIP6 simulations are not explaining the reanalysis. Is what's wrong? Is the reanalysis wrong, or is the CMIP6 wrong? What's going on there? And we'll talk a little bit more about that. And then if you likewise look at relative humidity and shear, I'll start with shear because it's easier. There's almost no change in trend here. The reanalyses are very similar. There is very little You could say maybe there's a slight decrease in the historical versus it, but it's not significant. In this graph over here, relative humidity, there's actually a more, if you just look at the actual CMIP6 runs, it actually has a more concise picture, and it's a more consistent picture, I should say. You see that the historical moves over to the right. There's higher relative humidity on average. The historical natural is showing almost no trend, but the reanalyses are showing completely different signs here. So it's kind of hard to understand what's going on there. And it's hard to understand whether the CMIP6 is reliable as a result either. So definitely focus more on the thermodynamic variables, SST and potential intensity, because at least there's consistent physical intuition and sign with the reanalysis data set. So just to go back to that potential intensity piece, there was a recent study by Keel et al., which actually looked at, again, these discrepancies between what we see in the trends in the upper troposphere, between the reanalysis and observations, and then the CMIP6 models. So this graphic on the right, let me just talk you through that, is you look at, on the x-axis, it's normalized annual tropical trend, linear trend from the period 1982 to 2014. And on the y-axis is height. And what you notice is that the orange, which is the CMIP6, you see that the near the tropopause, the temperatures are falling off much less, right? And you also see a very consistent picture in the lower atmosphere. Whereas what you see in the ERA 5 and the Mira 2 is that you see it falling off a lot more, actually. And you see actually that the tropopause, or what we would call some close to the outflow layer of a hurricane, is dropping off a lot more in temperature, which potentially could mean that that's what we're seeing in with potential intensity, because it is a indicator of the differential between the top of the atmosphere and the surface. We see that the trend in the upper atmosphere and the reanalysis data is very different than what we see in CMIP6. So we need to understand, for lack of a better phrase, which one is right here, because potential intensity is one of the strongest drivers or predictors of rapid intensification. And so we need to understand whether that reanalysis trend is kind of off on its own there as far as what we've seen in the last 36 years, or if the CMIP6 is kind of missing something important here, especially in the upper atmosphere, because that really will start to tell us, as long as we don't have climate models that can simulate, the strongest category 4 and 5 storms and rapid intensification, these environmental variables like PI are the best predictors of what we have for future storm behavior and intensification behavior. So getting that right is essential. So more work to be done in this space and understanding that. Does that make sense? Anyone have any questions on this graphic or in general?
I guess I'm really quick. If you go back to the temperature as a function of time, like things like that, maybe one more.
Oh yeah, sure.
I'm surprised on the difference in sea surface temperature between the two reanalysis data sets.
Yeah, so this is really interesting, starting in, and this needs further looking at. Starting around 2003, there is a clearly a step change. Yeah, that I'm not really sure what's going on there.
Because we also then see a step change to some extent in the PI as well. And of course, the surface temperature is going to impact the profile, which is going to impact relative humidity. So
yeah,
just kind of, it seems like a small difference, but it's actually a pretty large difference from a global average tropical mean. So
yeah, no, I understood. Yeah, I think that's a great point. I think that when we talk about trend analysis too, if it's going to be just if it's a systematic uptick also, then you could have a spurious slope there. So that's something actually to make sure that, what it's getting, that whatever's going on there, we understand what's going on there.
Yeah, have you ever plotted the same plot for like had ISP or something, like things that are typically used for PCMs and might be like.
Yeah, that's a good, I think that's definitely a good thread to pull to understand where that it's something to do with an ingestion of new observations, I think. Yeah.
You know what the stated uncertainty of either the analysis data sets is?
I don't know the stated uncertainty honestly off the top of my head, but
But it's larger than
yeah, for sure. Well, yes, I think that's probably accurate, sure. Yeah. All right, well, I'm actually at my last slide here, so I'll open up to questions after this, but hopefully this journey of going from, a future projection that maybe seems a little bit suspicious to seeing that same trend in observations and getting an idea that it might be outside of natural variability and having that environmental explanation hopefully gives a little bit of confidence that maybe this rapid intensification trend is a robust one. We've seen it in the Atlantic, West Pacific, and globally that there's pretty good consistency between, well, at least in the Atlantic and West Pacific, between the observational data sets. And all three of those basins, based on high floor, the anthropogenic contribution is definitely noticeable for how the tropical cyclones are intensifying faster. The recent years we see in a unequivocal fashion that the higher SSPs are being caused by anthropogenic drivers. It's a little bit more of a question mark with potential intensity because of those inconsistencies in the trend between CMF6 and the reanalysis data. But again, we see that there's a contribution there. This is something that I didn't kind of emphasize, but I brought it up at the start. The fact that we see these trends both in the tropical mean state as well as in the storm local state, there's a lot of literature out there, which is that storms track variability will change and maybe more poleward. But the fact that those more poleward years have not shifted storms to less conducive environments, and that the tropical mean trends are basically very similar to what we see in the storm local trends, suggests that these storms aren't running away from the nice environments, the hot tub situation. So that's kind of important. And then finally, climate change has likely already contributed to the larger proportion of RI. And as a result, it's probably time to start talking about how we build coastal resilience and improve forecast performance for these storms because of the risks they pose. And then I brought up at the start of this talk. So with that, I'll stop now. Hopefully there's time for questions. I know we started a few minutes late.
Yeah, well, we definitely have time for questions. So first, let's thank our speaker. So questions and yeah, and if you could repeat the question quickly, just to make sure that folks aren't losing it. Yeah, Brian.
Yeah, very, very the conditions for RI are obviously important in making sure that spells rapid intensification. The tropical cyclones are kind of a time integrated sense too. They have to go through some organization perhaps before reaching RI, which requires favorable environment. So I wonder how much effort has been to, instead of looking at the time of RI and the environment, just taking a step back and thinking about these TCs and how they have some preconditioning to get organized, and then they take off if the conditions are right. And I wonder if that's also important, is that before they get into those really favorable environments, or what you think would be favorable. So I'm thinking of it more of a Lagrangian timing and a time as opposed to this is the time of RI, what are the conditions and that sort of thing.
Yeah. So Brian just asked a question about whether or not some of the conditions before RI, rather than just at the moment where the RI starts, could play a bigger role or an important role in RI as well. That's a great question. I think it brings it. That has not been looked at in a methodical way in the climate sense. That's been looked at for forecasting. And normally how it's looked at is, rather than looking at the environmental conditions beforehand, they look at a persistence variable in the storm behavior, and that almost overwhelms it. But I think, and what I mean by that is what happened the last 12 hours and 24 hours in the storm. And they use that almost as a proxy for how the environment's been in the past. That normally becomes a leading predictor and it's correlated better with the past environmental conditions. I think there is something to be, there is a more methodical way that needs to be looked at those earlier time periods because of the fact that it's not always, because of intensity change detection issues too. Sometimes you miss it and you're catching up with your measurement technique as well. So I think there's definitely something to be looked at closer there. Thanks for the question.
Any other question? Yeah, Daniel.
Yeah, I have just an interpretation question. As you showed the probability for RI as a function of these environmental parameters, you showed it 4 or 5 are met when the probability increases by up to 22% for RI.
Yep.
Is that something I can say that for that storm, or can I say every 4th or 5th storm will undergo RI, especially your business to predict? Or are they are independent and I can put it on the overall and formula? And then my question is, maybe I missed that. Did you correlate the type of RI and wind speeds? I mean, the degree, how many knots increase to these events? It would be interesting. If 22%, is that only one case which goes up by 50 knots? Or is it 22%? Every case goes up by minimum 35 knots or something like that. So an extra correlation analysis is there. Then you would know, every 4th storm, minimum 30 knots. Every 10th storm, 80 knots.
Yeah. Those are both very, very good questions and great points. I'll just say that because we're doing annual values. Oh, sorry, this is further back. Because we're doing annual values and we're doing annual averages over 36 years. Like, it's one of those things that you'll see that even the operational version, which is like the ship's RI predictor, right? You'll have situations where everything seems right, but you'll have a miss. And unfortunately, until these values, or we come up with a way for this to be close to like 50 or 60%, I think that's an issue, right? You're adding some skill here. And the approaches, the statistical dynamical approaches have long outperformed dynamical approaches on RI as a result, because of these convergence of variables leading to a better predictability. Only now in recent years, like HWRF and some of the dynamical models that are run at high resolutions are starting to beat the statistical dynamical ones. So that is still a problem, right? This is not necessarily a predictability question at this point. It's more of a trend or commentary on how well these predictors are related to it, so that we can start to pull out climate trends. But that is a question, right? That from a forecasting angle, that is really important. That second point about partitioning, and I was just talking about this earlier, is this comment about marathon versus sprint rapid intensification. Is that I think that differentiating between those two is important in understanding what are causing those events where you see the biggest step changes, because those are the ones where you have the largest errors. I think more work needs to be done there. So yeah, appreciate that point.
So we'll go with Emmy and then Levi and then Malcolm, and then we're going to move on to lunch. You all raised your hand at almost identical times. So
Very interesting. So you mentioned a little bit at the very beginning about the large scale implementation, like AMO.
Yeah.
Did you find any research into analysis that the large scale is like a linear, like AMO, which makes it?
Yeah, so I have not done that, but I believe Justin Ning, who worked under Gabe Becky also, he has a paper on that topic, which is more of the seasonal predictability of rapid intensification. So yeah, I'll refer you to that. Yeah.
Levi.
You cited several papers at the very beginning, sort of showing how high floor did a good job. Number one, the TCs in general, I think, but then also rapid intensification, I believe.
Yeah, well, the rapid intensification piece was literally, I think, I don't know if anyone else in the GATL group besides myself has looked at that.
Well, the point is that high floor seems like it does much better than other global models.
Yep.
I know it's relatively high resolution, but do you know why do you think it's a better model for TCs than deep?
Yeah, no, that's a great, yeah, no, it's a great question. No, and I don't believe it. It's that question of like, all models are bad, some are useful.
You're using
Yeah.
the results. of it, so
Yeah.
I believe it in that sense.
Yeah, no, 100%. I think that the reason why I use it and believe it is because of its performance on historical metrics, and it does well. Why I think that as far as the model makeup, what makes it a bit, I think the model of how it deals with convection and its parameterizations for that is helpful in producing storms that intensify faster, especially the Atlantic Basin.
So do you think the parameterization for convection is a bigger factor than resolution?
I think they're both really important. I have seen now that global models that get down to the scale of this, and this is actually a problem because at 25 kilometers, there was probably one other global climate model that was getting RI in Cap 4s and 5s. Once you went down to like another maybe 10 or 12 in that ballpark, models now are showing up and past, obviously now that 3.75 kilometers, that's showing up RI. So I think resolution is definitely important. I think that the convection is also important. Is it getting it right for the wrong reasons? Potentially, but I think that with the way that it is helping us understand TCs and how it has been designed has been an effective tool because of the fact that it has passed the bar on so many different scales and levels that it gives me hope that it does provide some insight. Yeah. Sorry, that sounds a little pessimistic.
Yeah, Malcolm.
Just a little story you might be interested in since you're in the reinsurance business.
Okay.
Superstorm Sandy was really an example of slow de-intensification. Because what happened on the night of October 29, 2012, as the eye of the hurricane approached the shores of northern New Jersey, the wind speeds dropped below the threshold for a category 1, what's that, 71 miles an hour. And the National Weather Service downgraded it from a hurricane to extratropical storm. And then it hit the beaches, and that had some very interesting legal consequences because a week or so after the storm, I got a call from Lloyd's of London, who were the reinsurance company that was insuring Alliance, which was the American company that was insuring a casino and a pier off the beach in the water and a fun park. There was a roller coaster and a big Ferris wheel, and it all came crashing down that night and became a picture that became iconic. And so Lloyd's of London said to me, when did all that come crashing down? Was it before 7 p.m. or after? Because if it was after 7 p.m. and it was not a hurricane, then the American company Alliance should not have paid out the 20 million. They did. And they wanted to say, well, Mr. Bowman, when did it all come down? And I said, well, it's a casino. What did the security guards have to say with their eyewitnesses? They said, no, they all ran for their lives. I said, well, it's a casino, there must be security lights. And they said, no, the power went off. And I said, well, this is a tricky question. But I looked at offshore wave heights and wind speeds, all the rest of it. And in the end, I said, I don't know. And I knew that going into it. I said, so I wrote my report. And they didn't want to pay me. I had to go to London to make a personal trip to get paid. But I thought that was a kind of interesting story, which different from what you're talking about, but
No, honestly, I mean, I'm all about interesting stories that are off topic. I love it. So I appreciate that. It's also because of that event that you were mentioning, the definition of loss payouts changed and how the National Hurricane Center deals with those storms, all because of Sandy. And actually, there were winds that were hurricane strength. The problem is that it lost its warm core features. And so they lost its title as a tropical system at that point. But yeah, no, it's a fascinating topic when science interfaces with these financial instruments and payouts that are, 20, $30 million, things like that. Thank you.
So maybe now I'm going to take the host prerogative and ask one quick question, which can kind of be a yes or no, but related to Sandy, which is a good suggestion, right? That wind speed isn't necessarily the best metric for understanding risk and potential damage, right? So there's been a lot of work to suggest that actually sea level pressure, particularly central pressure deficit, is a better indicator of damage. Have you tried to replicate any of this work with changes in central pressure and quick changes in that?
Yeah,
as opposed to wind speed?
Yes, the answer is yes. So the only problem with that is that it's tough for AT HRSAT.
Yeah.
Doesn't have that, right? It's the wind is from the pressure, but yes, the answer is yes, I have done that. That's something that I am planning on, figuring out what the best way to show that. I don't think it's good enough to be a separate paper, but in general, you see a lot of the same trends. Okay. But in the Atlantic, actually, the trends are not as significant. So, especially when you bring in Ivy tracks, you do the last 40 years, now that we have 1982 to 2021, now 2022, that trend in the Atlantic is not as significant as it is with the wind data, which is an interesting result. Globally, the results are still significant and a lot of other basins, but in the Atlantic, it's not. I haven't looked at whether or not it meets the significance threshold yet, but it's definitely a smaller trend with pressure.
All right, so we're going to head over to lunch now, which is over in Challenger. And this is just a reminder that from 1:45 till 2:30-ish, graduate students have time to just meet with Kieran on their own, also in Challenger. So let's thank Kieran again, and I hope to see you all at lunch.
Thank you, guys.